Hey everyone, in this video we're going to be talking about how to graph sine and cosine functions when there are more coefficients involved in our functions. Let's recap one of the slides in our last video, talking about this general strategy of plotting exactly one cycle of a trig function so that we understand the pattern that's going to be repeating infinitely many times. And our goal in this video is to address functions that look like 3 times sine of x divided by 2 and negative 2 cosine pi times x minus pi. So of course, each one of these numbers involved in our trig functions is doing something to the overall shape of the graph. So the quantities that we're going to define below are going to give us an idea of what characteristics of the graph are actually being changed and how we can incorporate those into our graph. So suppose that I have constants a, b, and c, where a is not equal to 0 and b is strictly positive. Here define f of x as a times sine of bx minus c, and g of x as a times cosine of bx minus c. Then f and g have what are called amplitude, period, and phase shift. Amplitude is defined as the absolute value of the coefficient a out front. The period is defined as the number 2 pi divided by b, b being the coefficient of x, and the phase shift is defined as c divided by b, where c is this constant term being subtracted from bx in both the sine and the cosine functions. Now each one of these quantities does have a graphical meaning. The amplitude refers to a vertical stretch or compression. And the period, like we talked about in the last video, is the length of the interval for which one full cycle of the graph happens. And the phase shift you can think of as a horizontal shift from the left or to the right. And by shift, we really just mean we're pushing the graph left or we're pushing the graph right, all depending on the sign of the constant term c. So we're going to start off with the function f of x equals to 3 halves times sine of x. We understand that the sine function normally has an amplitude of 1 because it stretches from 0 to 1 and then 0 to negative 1. It turns out that the sine and cosine functions have some default understandings. They both have a default amplitude of 1, a default period of 2 pi, and a default phase shift of 0. So when we look at f of x equals to 3 halves sine of x, the only thing that's changing is its vertical shift or its amplitude. And the way that we're going to graph this is the following. Let's go ahead and sketch one cycle of the sine function so we can kind of have an understanding of what we're dealing with. As we said before, we want to try to transform one cycle of the trig function so that we can understand what the entire graph looks like. So using our formula, we see that the amplitude of f of x is going to be the absolute value of 3 halves, which is just 3 halves, which we need to note is bigger than 1. Whenever our amplitude is larger than 1, this is going to give us a vertical stretch. In other words, our graph is going to get vertically taller. So on the right, we're going to sketch our sine graph again, but I'm going to do it with some dotted lines just to think of it as I have a shadow of my graph. I'm using it as a reference so that I understand what f of x is going to look like. Since we have an amplitude of 3 halves, I'm going to draw the tick marks on the y-axis of 3 halves and negative 3 halves. And then I'm going to vertically stretch the dotted line function so that I can get our actual function, or at least one cycle of it, f of x equals to 3 halves times the sine of x. So the strategy that we're using really goes as follows. I've sketched one cycle of the default sine graph using some dotted lines, and then I tried to vertically stretch it to account for the amplitude of our function f of x. Overall, I think this process just makes it a little bit easier to see what your graph needs to look like. And it's not too hard to visualize a sketch when you're just superimposing one picture on top of another. And so the graph that I have here is just one cycle of f of x. And now that I know what it looks like, all I need to do is just repeat this cycle infinitely many times on the left or on the right. So to continue the pattern, I can just draw it in the following way. I can continue that curve on the left and right and just give it some dotted lines to say that this shape just continues forever. And this is going to be the graph of f of x equals 3 halves sine of x. Now I made it a point to mention that the amplitude is a number bigger than 1, which gave us a vertical stretch. Suppose now that I actually had the graph g of x equals to 2/3 sine of x. The number 2/3, which is going to be the amplitude of this function, is less than 1. And whenever I have an amplitude that's less than 1, this actually gives me a vertical compression. So what we're going to see is our graph gets vertically shorter as opposed to the example that we just did where our graph got vertically taller. So I'm going to sketch with the dotted line one cycle of the standard sine function once more and then superimpose it with g of x. We're also going to put tick marks on our y-axis of 2/3 and -2/3 because those are going to be our new upper bounds and lower bounds. And when we vertically compress this graph, we're going to get the following picture. So for some comparing and contrasting, the second graph got vertically shorter while the first graph got vertically taller, and this all has to do with whether or not our amplitude is bigger than 1 or less than 1. But now that I have a full cycle of g of x, I can repeat that shape on the left and right to get a sketch of the full graph, like so. So again, just to recap the entire process here, we're drawing one cycle of the default sine function, and then we're superimposing it with the transformed version, because each one of these values, like 3/2 or 2/3 or anything therein, is just taking our standard sine function and stretching it, compressing it, moving it. It's doing some kind of transformation to the shape. And I think that this process just makes it a little bit easier to see what those transformations are and how I'm going to repeat this cycle again and again on the left and on the right. For our next example, we'll graph f of x equals to 3/2 cosine of 2x. Now we are recycling a little bit here because I'm using that amplitude of 3/2 again, but two things are changing. First is that we have a cosine graph, so we need to understand what the cosine full cycle looks like. And now I have a coefficient of x, meaning that I'm going to have a period that isn't equal to 2 pi. In fact, when I use the formula, our period is going to be 2 pi divided by b, and since b is equal to 2, I have 2 pi divided by 2, which is just pi. This means that I'm drawing, at the end of the day, a full cycle of the graph on the interval from 0 to pi instead of 0 to 2 pi. So let's go ahead and sketch out a full cycle of our cosine graph. One cycle of our cosine graph, drawn on the left, looks like the following. And then on the right, I'm going to do a dotted line version of that graph so that I can superimpose it with f of x. Now we're going to draw this function in two stages because otherwise our graph would get a little bit too busy. But first let's go ahead and try to vertically stretch our graph by taking into account the amplitude. Just like before, I'm going to put 3/2 and -3/2 on my y-axis and then observe a vertical stretch to make my cosine cycle adhere to those values. So now we've seen that it's gotten vertically taller. Now for the next stage, that's where we're going to take care of the period of this graph, which is happening on a shorter length interval than 2 pi. This is now happening on an interval of length pi, which is half the length. So I am basically compressing my shape horizontally by half. And certainly your own pictures don't have to be this detailed, but I'm drawing a couple of arrows just to remind myself visually that I'm taking this shape and I'm pushing it towards the y-axis. One way to think of it is that you have a spring in both your hands. You're going to leave your left hand fixed like it's the y-axis, and your right hand is going to account for a stretch or compression. So I want you to imagine compressing that spring by half, and that's going to be our third picture. So let's go ahead and sketch things out and label this up. I'll still draw my standard cosine cycle with a dotted line, and I'll superimpose my y-axis with my positive 3/2 and my negative 3/2. And then I'll put the value pi on my x-axis and draw our cycle from 0 to pi. And like we said, this is going to be a little bit taller because I have a vertical stretch, and now it's going to be thinner because I have a horizontal compression. And this is the shape that we're going to get. We can see that this is still the same shape as our dotted line after I have compressed it horizontally and stretched it vertically. But now that I have one cycle of f of x equals to 3/2 times cosine of 2x, I can simply just repeat this pattern again and again from the left and to the right, and then I have the full graph of our function. Alright, so we're only going to do two more examples in this video. First, consider g of x equals to -1/2 times the cosine of 2 pi x. Quickly, we can go ahead and compute our quantities. The amplitude is going to be positive 1/2 because I take the absolute value of that outside coefficient. The period is going to be equal to 1 because our coefficient of x is 2 pi itself. And so we're going to be graphing this on a cycle from 0 to 1, which is a much shorter interval than 0 to 2 pi. To give you kind of a point of reference, 2 pi is equal to about 6.28, so graphing this on the interval from 0 to 1 is a much stronger compression. And just like in the last slide, we're going to do this in two stages. First, we'll deal with the amplitude, and second, we'll deal with the period length of 1. Let's go ahead and get up our sketches. We're going to draw the cosine function, or one cycle of it, both in full and on a dotted line version. Now something new happening is the following. The coefficient right out front is -1/2. That negative sign does have a graphical implication. It turns out that that is going to flip my function about the x-axis. You can think of the x-axis like a skewer, and I'm spinning about that skewer. So it's going to turn my function vertically upside down. And I've drawn a little arrow to help give us that indication. But just like before, I have a positive and negative 1/2 on my y-axis, so I know how tall, or in this case how short, to draw our cosine curve. So once I imagine flipping this curve upside down vertically and compressing it, I'm going to get the following picture. So that amplitude of 1/2, which is less than 1, says I have a vertical compression, and that negative sign out front says I have a vertical flip. Now for the next stage, let's go ahead and get our graph ready. I don't necessarily need to make this the most accurate picture in the world, but I need to have some idea of where the number 1 sits on the x-axis relative to the other x-intercepts. We know that that first x-intercept of the default cosine function is happening at pi divided by 2, which numerically is about 1.5 and change. So at the end of the day, we are going to compress our graph horizontally, and we're going to compress our graph vertically. So my graph should be bouncing between positive 1/2 and negative 1/2, and I should see an entire cycle happen between 0 and 1. And once I complete this picture, I'll get the following cycle. And just like always, we're going to repeat this shape to the left and to the right, and since this is such a small cycle, I'm going to do it a whole bunch, but this is going to be the graph of g of x. The two biggest takeaways are the following. It's good to graph these in stages when you have to worry about a different amplitude and a different period. Further, whenever I have a very small compression of the graph, I just got to be a little bit careful about the drawing, make sure that I'm drawing it in a way that it's readable. That's why drawing each one of these graphs with the default sine or cosine function kind of dotted in the background is really helpful because it gives me a reference as to how big or small our graph should be. And the second is what to do when I see a negative sign out front. That negative sign means I just have a vertical flip of our graph. In our last example, we'll graph a function that actually has something going on with phase shift. Here we can go ahead and compute our standard quantities. We have an amplitude of 2 and a negative sign that says I have a flip, and we have a period of 2. But now I have a constant inside that says that I have a non-zero phase shift. So we're going to see how to deal with that in this video. Using the formula for phase shift, which is c divided by b, we'll see that we have a phase shift of positive 1, a number that is strictly bigger than 0. Our formula at the very beginning slide has a negative sign installed into it, which tells me that when I'm taking my c value, I change the sign from the actual function. Here I see negative pi, so when I record my c value, I'm going to think of it as positive pi. Just to play the what if game, if my function had f of x equals to pi x plus pi, then I would have a c value of negative pi. It's kind of like using the quadratic formula or when we were doing vertex form. It's one of those places where you have to change the sign of the value you're trying to look at. Alright, so let's go ahead and do our standard setup. We have one cycle of the sine function, and we know that we're going to stretch it up by 2, and we're going to have a vertical flip. Moreover, this function has a period of 2, so I have to compress one full cycle on the interval from 0 to 2. So incorporating all of these changes, I get the following cycle. It has my flip, it has my vertical stretch, amplitude of 2, and it has my horizontal compression, a period of 2. Now it is recommended that the viewer do this in more than one step. I've only done this in one step here because I wanted to fit the entire example onto one slide, but you should do a separate step rather, where you're doing the flip and the amplitude, and then a separate step for the period, just so you can get this one cycle of the function at this stage. Now what I've graphed here is the function negative 2 times sine of pi x. I haven't accounted for the phase shift yet, and that's going to be our third and final step. So here's the thought process. Normally I would graph one cycle of this function on the interval from 0 to 2. That's kind of our starting point. You always start things at 0 and go for the period length, but now we have to push this interval down the x-axis a little bit. We know that we have a phase shift of 1, so to get a sense of where this thing needs to be graphed, I'm going to take my interval from 0 to 2, and I'm going to add a 1 to each of the inputs. This gives me the new interval to graph on, the interval from 1 to 3. And just so we're on the same page, the interval 0 to 2 comes from our default strategy. We always graph one cycle of our trig function on the interval from 0 to p, where p is the period of our function. In this case, p is equal to 2. So the second step, that second graph, we have one cycle graphed from 0 to 2. But now that I have a phase shift, a horizontal shift to account for, I'm just picking my graph and moving it to the right. So that's where this interval 1, 3 comes from. I've taken the interval 0 to 2, and I've added a 1 to each one of the endpoints. But now that I have these values, let's go ahead and sketch out a few things. Let me put the values 1 and 3 on our x-axis, and now I know that one full cycle, namely the exact same shape that I see above and to the right, I'm going to put that shape starting at 1 and ending at 3. And so now that I have a full pattern, let me go ahead and repeat this pattern again and again so I can get the entire graph. So this example clearly had the most number of steps in the whole video, because we had an amplitude, a period, and a phase shift to account for. So it's really recommended that you try things like this, and maybe try the examples in this video again on your own by doing one at each individual stage. This probably is the most straightforward process by just letting one cycle of your sine or cosine function undergo one transformation at a time. By transformation, we mean a vertical stretch or compression by our amplitude, a horizontal stretch or compression by the period, and then a phase shift where we simply just add or subtract a value to the endpoints of our interval. Our phase shift value here was positive, so we did a right shift. If I got a negative number, I would have done a left shift. Alright, well thank you so much for watching. Please reach out if you have questions, and have a good day.